Since the Industrial Revolution, new technology has helped American manufacturing grow into world leadership. But today, many industries have lost their competitive edge. Can the new technology of advanced automation turn things around? What is this new technology? How does it work? NOVA examines the robot revolution and the future of the American workplace.
Major funding for NOVA is provided by this station and other public television stations nationwide. Additional funding was provided by the Johnson & Johnson family of companies, supplying healthcare products worldwide. And Allied Corporation, a world leader in advanced technology products for the aerospace, automotive, chemicals, and electronics industries.
Through the 19th century, America industrialized. New machines expanded the productivity of workers. America developed into one of the world's leading manufacturing countries. With the 20th century came new technology, the machines of mass production and the assembly line. This country grew to lead all others, both in its productivity and prosperity. Yet today, certain sectors of American industry are bankrupt. In the last decade, 2 million manufacturing jobs have been lost. More than 1,000 companies have closed. America, once maker of half of the world's steel, today imports a third of her needs. Some blame management or the unions. Others blame obsolete manufacturing methods and equipment.
The basic moral of the story is it's the fault of everybody. You can't build a world-class economy without world-class inputs. And if you look at any of the inputs going to American industry, the skills of the workforce, the qualities of the managers, the amount of capital equipment, the research and development, American industry doesn't shape up on any of those dimensions.
And then there's foreign competition. Today, the United States imports 25% of her cars, 40% of her vacuum cleaners, 100% of her video cassette recorders. Foreign productivity and ingenuity are challenging American preeminence in mass production.
I think that the real problem in the competitive area at the moment is the United States is in that denial phase. We see ourselves being beaten up in international competition, and we jump to the conclusion that somehow the rest of the world's doing it by cheating. The Japanese are being unfair. There's nothing unfair about a cheap, high-quality product. That's what the game is all about.
The American economy is in transition. Old industries are dying. Foreign products, cheaper and of better quality, are taking over American markets. Yet revolutionary forces are on the move, heralding a promise of rejuvenation. The forces of computer-driven automation. Ranging from computer-aided design to computer-programmable robots. Computers manipulating information. Computers controlling machines. Is this new computer technology the means for America to revitalize? To produce better quality goods at lower costs than countries abroad.
We have over 500 computers supporting this manufacturing process in this plant. 4 years ago in our company, we had less than a dozen computers supporting manufacturing in its daily production of its goods. That is the explosion of science.
How far can computer automation deliver the benefits to America of greater productivity, improved quality, reduced labor costs, and more manufacturing flexibility? But yet, how far could computer automation change and disrupt our society?
Obviously, change is inevitable. I think obviously we'll see a lot more computer technology. The real question is, what is the character of that technology going to be? How are these machines and systems going to be designed, and what will the role of people be in the workplace of the future?
This program will examine the technology of computer automation, how far it's being introduced, and the choices it presents both to industry and society. The choices between different systems and how they might be developed to reap the greatest economic benefits with the least social cost.
We have an unprecedented array of choices before us. We have an unprecedented potential to use computers and computer-based automation in a way that benefits the society as a whole. I think it would be tragic not to seize that potential and use these technologies in a way that in fact do bring real benefits.
Already, computer automation is appearing in offices and factories, and the key element in this new automation is the computer. A computer, simply, is a device which electronically stores information or data. The data might be numbers, words, or images. This data can be manipulated according to a set of mathematical rules called a program or software. A program can multiply numbers, generate text, alter images, or send electronic commands to machines. All processes previously done by human hands and minds. Computers first appeared more than 40 years ago. Since then, they've been getting cheaper, more efficient, and much more powerful. By the early 70s, many organizations had installed a computer, probably in the basement, to help with financial or personnel records. These computers were cost-effective for large bureaucracies. Still, they had little impact on the way most Americans worked. Then, in the mid-1970s, came the microprocessor, a whole computer packed into a tiny chip, and computers passed a watershed. Now they were small enough, cheap enough, and powerful enough for a host of new applications which might help revitalize American manufacturing in the nick of time.
In the second part of the 1970s, we began to hear about the fact that other countries were beginning to be as productive as we were. We began to see many foreign goods coming into the country, especially electronics, automobiles, so on. This was perceived as a threat, and people looked around for some response to this threat. Well, the microprocessor had just become fairly readily available, and so people reasoned that we could possibly bring this computer power to bear in the manufacturing environment by having these microprocessors direct machines to do things that they could never do before. We began to look into having microprocessors direct robots, which could conceivably work day and night producing products, and this was going to help us with our productivity problems.
Robots are computer programmable mechanical devices. These fluid-moving robots are symbols of the extent of computer power. They mimic human actions. By the mid-1980s, computer-controlled robots needing no coffee breaks, safety regulations, or unions were replacing some of America's 20 million workers. This type of robot was hyped by industry and the media as the great savior of manufacturing. But there are only 15,000 robots in American factories today, directly displacing perhaps 20,000 workers. Most robots are in showcase factories of large companies like General Motors, John Deere, IBM, Chrysler, or General Electric, whose managements are willing and able to make investments of many hundreds of millions of dollars. However, such robots have shown limited cost effectiveness. They're used primarily in spot welding and paint spraying, where protection against hazards make it particularly expensive to use human workers. But robots are not, of themselves, the key to computer automation. They're only a peripheral factor, because the great advantage of computer automation centers on the computer. The computer can not only control machines, but it could also control the organization of a factory. Organization control is where the greatest benefits of computer automation could be achieved. Already, the computer has started to revolutionize the control of office and service organizations. Here at the New York Stock Exchange, productivity is up 400% because the computer network electronically stores, tracks, and records data. Before computer automation, the paper-bound records could lag far behind on even a quarter of present-day business. Today, more than 10 million computer terminals are used in offices across America, from banks to insurance companies. They track, store, and manipulate data electronically. 2 out of every 3 office workers use some form of computer-based machine at some time during the day to help them streamline their work. In Boston, for example, they've installed an $18 million computer system to help run the city electronically.
It's a very old city. We have to maintain birth records, assessing records, deeds records since 1629. For that public information to be available to either historians or people who need to utilize that in their daily work, it has to be readily available. And right now there isn't enough physical space in the building to actually support that kind of public information.
The Weights and Measures Department at City Hall is a holdout, not yet computerized. It's paper-bound. Here, clerks must still dig out information buried in banks of files and hand process it. This is the city mainframe computer. It electronically stores almost all city records and data. The mainframe is the center of the Boston Automation Network. It links every city department and the school, hospital, and police offices. Data can be channeled electronically between a dozen different departments and can be punched up in seconds. For example, before computer automation, Boston had had to declare a moratorium on unpaid parking tickets. They couldn't deal with the paperwork. Today, at any city terminal, they can compare the tax records with public works needs, or birth records with school enrollments, and much more. The Boston City computer system replaces paper handling with electronic connections. Each department can have immediate access to all others, and to the mainframe data store. It allows this large organization to be controlled more efficiently. In the same way, computers can boost control efficiency outside the office, in the much more complex field of factory manufacturing. Factory manufacturing is a complex of separated sectors of work, divided by barriers of understanding and working methods. There are the sectors of design, testing, fabrication, assembly, inspection, and materials handling. People from clerks to managers doing reams of paperwork bridge the sectors and tie the operation together. Computer automation is appearing independently within each sector, varying from rudimentary to advanced. For example, this is a computer-aided design terminal. The computer stores and manipulates design data, eliminating the hand-drawn design. This is an example of computer-controlled assembly. The computer sends command data to robots spot welding cars on the assembly line. This is a computer-automated materials handling system. The computer processes data to direct automated carts moving materials on the factory floor.
Manufacturing is a very complex activity, and we've tended to deal with that complexity by breaking it down into smaller, more manageable parts. We develop these islands within the factory environment, and we automate those islands, but the integration between those islands has yet to happen.
Despite computer automation within sectors, white-collar workers must still do the paperwork, passing information along to keep the factory running and deal with breakdowns and disruptions.
That's pretty much where many companies are today, with islands of automation, and it's the integration of those islands that really will bring the productivity gains in the future.
Automation experts foresee the greatest productivity gains coming from replacing people and paper with computer control. Computer-integrated manufacturing. SIM. Computers linking every factory sector together. Computers monitoring for breakdowns and disruptions to create a workerless, paperless factory. We will now investigate the extent of computer automation within each factory sector and the possibilities of computer links between them. We start with design. Design drawing has long been the basis for manufacturing. But like the old-fashioned office, it's paper-bound. Unlike electronic computer data, it can't be manipulated, processed, and analyzed in fractions of seconds. Drawing is labor-intensive, and it's beginning to become a thing of the past. This is a computer-aided design terminal, a CAD terminal, a tool to automate design work. Instead of a pencil, the designer uses a light pen to pull lines and curves out of the computer. He's constructing a spindle for a car disc brake. He can also pull previously designed parts out of the computer memory. Using this tool, there's no need to search through blueprint libraries or transcribe what has been done before. No need to reinvent the wheel. At a touch, a wire mesh outline becomes solid. It becomes a cutaway, a blow-up. An assembly explodes into its parts. Within a solid image lies its wire mesh foundation. In reality, computer design isn't as simple as in this idealized demonstration, which took many hours of setting up. Nevertheless, it's used extensively.
Computer-aided design systems are used extensively today, from the very largest of companies even to small companies. One reason for that is that computers themselves started in an office environment many, many years ago. It started with things like payroll and accounting, and then gradually got into the technical side, got into the engineering and design, and only now are starting to go into the manufacturing side of the operations.
At General Motors, a leader in automation technology, they're using more than $100 million of CAD systems for original car design work. A typical car body involves over 5,000 elements. Using CAD, these elements can be interrelated, adding to the exterior framework, interior items from the firewall to the steering column. Design items can be tried out in seconds.
CAD systems generally bring to companies productivities typically 3, 4, or 5 to 1. And these represent real savings in terms of the time it takes to generate a design, the amount of work, the amount of designs that can be done in a given period of time by designers. So these are the kinds of gains that we see, 3, 4, 5 to 1.
Whatever the benefits of computer design, it would seem that manual drafting will become as anachronistic as the slide rule in this phase of manufacturing. The questions of productivity and jobs are also reflected in the next stage of manufacturing automation: testing. Road testing a car, for example, might become a thing of the past. The data from these tests might, in the future, be derived from a computer engineering simulation. This engineer is simulating the mechanical testing of designs and analyzing structural stresses. She's examining a version of the real-world behavior of a product before it's built. This is a stress analysis of a wheel. Through an overlay mesh, the stresses are analyzed in each tiny segment to reflect the distortions in a wheel running over rough ground. The engineer at the computer looks for the effects of vibrations, friction, and fundamental frequencies. The engineer at the computer could replace the test driver. But many aspects of computer testing are experimental. This sector of automation is far from developed. The computer would have to know all about every possible stress a car might suffer on the road to fully automate this stage of manufacturing. After design, a product is fabricated. Fabrication is the next step in the industrial cycle. It takes us to the factory floor, where machines cut and shape parts to make, for example, some of the 5,000 components of an automobile. Programmable automation to control these processes started decades ago.
It's interesting that about 30 years ago, when this kind of automation began, the machine instructions were stored on this kind of paper tape. So it would be the machinist that was essentially responsible for taking the design data and making this piano roll kind of tape, which gives both the geometrical positions of the component, and it also governs the machine speeds and the table speeds, the speed of the machine. Nowadays, we don't need to use this older style. We can program the information directly and on the console here on the computer.
But the programming still depends on the machinist, who might have to be retrained for this job. He uses his knowledge and experience of metalworking and tools to translate design data into machine commands. The John Deere tractor plant in Iowa is a showcase for such computer-automated fabrication. It represents what can be achieved with today's technology, $500 million, and a management which is willing to take the risk. But this automated machining floor is one of only 30 such installations in America. Here, 6 computer-programmable machining cells shape engine blocks. They change their parts to do a multitude of different jobs, one after the other, untouched by human hands, controlled by computers. They save in setting up time. There is less scrap. The quality is more consistent. Inventory can be cut by 2/3, lead time by half. The overall gain in productivity, Deere says, has been hard to quantify, but systems like these generally improve productivity 20 to 30%. And most importantly, they can quickly change from making one type of part to making a different type of part. This flexibility is the big bonus of computer automation. A whole variety of custom products can be made at mass production prices.
Previously, before the advent of the computer, that manufacturer, if he wanted to change product, to change his machine, had to do it mechanically. He had to change fixtures and tools and make these mechanical changes. What we see now, and certainly even to a greater degree in the future, are these changes coming about by changes in the software, by reprogramming rather than refixturing and retooling.
Yet reprogramming still calls for the machinist craftsman to use his knowledge and expertise to translate design blueprints into computer commands. One step toward the factory of the future would be to incorporate the craftsman's expertise into a computer.
The craftsman understands about the sloppiness of the machine tool, or how the tools will deflect, or how the fixtures might move whilst the component's being machined. And he does things like look at the chip color, and he looks at the way in which the surface finish on the component is being formed. Now, once we begin to get some of that data into the machine, then we'll be able to do this hands-off thing much easier, and we'll begin to move towards what you might call an expert system for machining. Now, an expert system is a computer program which contains all of the geometrical knowledge and all of the material knowledge, plus all of this craftsman knowledge, and it can begin to do some thinking or some inferences about the machining environment and the manufacturing environment. But once we have all of those rules of thumb that these craftsmen have built up for many years, also embodied in the electronic form, then we'll be able to do this unmanned machining much more easily.
While such expert systems are not generally available as yet, on this factory floor, the traditional machinist no longer has any place. Only about 10% of machining is computer controlled in the United States, but it might already account for as much as 50% of the value of all machining work. It means higher productivity and fewer employees.
Believe me, automation and robotization...
And though numbers are difficult to assess, it's easy to see why workers are worried. Union leaders consider this a major issue.
We're going to see a drastic change. The jobs that we have now are going to become as obsolete. As a matter of fact, 15, 20 years from now, somebody's going to look and see a picture of how we work, and it's going to look as obsolete to them. It could be your children or grandchildren. It's going to look as obsolete to them as a horse and wagon looks to us. But how many people out here actually feel that this is a problem in the future and that our jobs are being threatened in the very near future? Raise your hand.
Among many conflicting reports, the Bureau of Labor Statistics projects a shift from high-paid manufacturing to low-paid service work over the next decade. With 4 million manufacturing jobs lost due to automation and other factors, while 10 million service jobs are created.
We could, in fact, see a very likely scenario where the society becomes increasingly polarized, where many of the best industrial jobs, for example, are eliminated, and the only jobs that remain are those jobs that it's not worth automating, low-paid, dead-end, short work time jobs. If the technology is going to victimize people, they're going to fight against it. They're not fighting against technology. They're fighting against something that victimizes them.
I'm not discouraged by computers. I'm threatened by them.
But like Angie said a little while ago, hey, you look at that computer and you say, you're my mortgage payment. You're my car payment, right?
That's the truth.
I'm going to beat you, and I'm going to learn how to run you. If it means my job, I'm going to do it. But for God's sakes, give us the opportunity to learn.
People simply have to be retrained and reassigned. It is what I would call, sir, a relocation of people and a re-understanding of what their function is.
As long as they could continue to give me job security, then I would be happy. I don't want anybody to tell me, Bob, this computer is going to do your job. It's been nice. Good luck.
Some large companies like General Electric have retraining programs, but like automation itself, this is the exception rather than the rule.
It went from tubes into transistors and diodes. At that time, it was a little more difficult. You needed new equipment.
Retraining concerns tend to come after the fact rather than before. In America, unlike other countries, there's no national strategy and little government help for these efforts. But even the strongest advocates of automation believe that at the company level, consultation between management and labor could ease the introduction of computer automation.
I think that the planning process that involves all of the parties concerned, senior management, middle management, the working level, should take place as early as possible. Particularly the working level people should be brought in early so that they can see the computer automation not as a threat to their jobs, but indeed as a way for that company to more effectively compete in the marketplace, and in fact to create more jobs by growth of the company and by producing better quality products at lower cost.
However, computer automation has barely touched American industry. Many companies have balked at the capital expense. There are still 20 million factory workers and only 15,000 robots.
Even the leading companies, the Fortune 500 manufacturing companies, have applied computer automation no more than 5 or 10% of the potential that they can apply it.
Indeed, in assembly work, the next sector of the manufacturing cycle, at this John Deere Showcase automation plant, they haven't brought in robots to replace assembly line workers. Why? To find out, we must look at computer-controlled robots and understand their abilities and their limits in replacing human beings.
The simplest kind of programmable robot is a point-to-point machine. It'll be programmed to go from one fixed XY position, say along a track, to another fixed XY position, and it will be doing a pick-and-place operation during that motion.
This is a computer-controlled pick-and-place assembly robot with 3 degrees of freedom. Its movements are simple, and it can be reprogrammed to work in different configurations. The Japanese have made these simple robots their main investment. 70% of their 50,000 robots are of this type. Only 40% of America's 15,000 robots are as simple as these.
At the next level up, we have a machine which has a greater number of degrees of freedom in the overall working system. For example, the base, which is rather like the human shoulder, the elbow, rather like the human elbow, and these wrist joints here enable this machine to obtain 6 degrees of freedom. And so this can go over a more complex path and do things like spray painting and spot welding.
These are computer-controlled robots with 6 complex joints, designed to imitate human arms. They inherit the same limitations. They move no faster than human arms. They are not precisely accurate, and they're limited in the loads they can carry. And if an error puts the work in the wrong place, they never know it. They continue on mindlessly, but they don't do their job.
Another important factor is that robots are much more expensive than people in general. A robot will cost about $50,000, maybe more. It'll take another $100,000 in order to install it, and if you're lucky, it will do the job that one person will do. Now, if you're talking about competing against someone in a foreign country who's earning maybe $4,000 or $5,000 a year at the most, you can see that the robot will be worn out long before it pays for itself.
But regardless of cost, are human-like robots the best way to automate assembly work? What tasks would they have to be able to do?
For our tasks, it's very easy for me to do, something like putting a nut on a bolt. It would be very difficult for a robot to do. In order for me to do it, I need to be able to sense the contact between the nut and the bolt. I can tell from the feedback I get through my fingers, whether the nut is the right size for the bolt, whether the threads are crossed. For a robot to do a job like this, it would have to process a very large amount of sensed information. It would have to sense this contact. It would have to be able to sense the torque so that it knew the threads weren't crossed. It would have to allow the nut to move down along the bolt while it was turning it. One of the reasons that people study this is because they're interested in how they do these tasks, and by studying how a robot might do them, gives them some insights into how people work. There's an important distinction, though. We have to realize that this isn't necessarily going to be important for manufacturing. Duplicating what humans can do isn't going to be terribly productive in the manufacturing environment because we already have humans that can do it.
Indeed, in Detroit, human welders still work in parallel with robots when awkwardly placed or specialized welding is needed. It's difficult to conceive of a cost-effective robot that could connect cables on this assembly line.
The idea that robots should be complex has grown directly out of the fact that most of the American robots developed through artificial intelligence laboratories where the goal was to mimic human behavior. In fact, human behavior is not particularly what you want to mimic in a factory.
Nevertheless, certain factory applications will come out of university laboratories. At the University of Utah, scientists are building the kind of humanoid robot which Professor Searing wouldn't advocate for today's factory. They work in artificial intelligence, trying to understand how humans function by building a hand which mimics the dexterity of a human hand. How is it constructed?
Well, it essentially has to have the four subsystems that we talk about within this dexterous hand. It has to have structures, which are bones, tendons and muscles, which are the actuators, sensors to detect angles of joints and the contact with objects, and a central control system to manage the whole system.
In short, to make a useful robot hand, you have to make most parts of a person, including the brain. But concentrating on the hand, these are the muscle tendons. They run over a complex of pulleys pulled by tiny hydraulic motors to move each finger. Fiber optics measure the joint positions for feedback to the control center, which governs the speed and the stress on each tendon, as well as coordinating all the fingers so that the hand might do a useful task rather than move spastically. But what objectives can such pure research have?
It has two objectives only. It shouldn't be judged as a manufacturing device because its first goal is as a research tool for people in artificial intelligence and other areas of robotics to begin exploring dexterity while supervising a device that's quite rich in its degrees of freedom and sensory capabilities.
I think it's important to recognize that the universities have an important role to play in the area of robotics and computer automation. And that role is properly at the leading edge of the technology.
So while research looks to the future, today on these assembly lines, human hands and brains are likely to remain more cost-effective than any complex, expensive robot. A more effective approach to assembly automation is, where possible, to change the product.
Redesigning the products which we now assemble manually so that they're easier to manufacture is much more important than building robots that have all the capabilities of the human being.
In Lexington, Kentucky, IBM has set up a $350 million showcase automation plant. They've redesigned their new electronic typewriters from scratch so that they can be assembled using simple robots. The parts to be assembled are pre-sorted. The robots need simply pick and place.
We're seeing a lot of companies put a great deal of effort into both designing new parts as well as redesigning old parts so that simple pick-and-place robots can be used in the manufacturing of those parts rather than the more sophisticated and complex machines that are just expensive to bring in and difficult to support.
Traditionally, products have been designed for efficient function and human assembly. It's a radical departure to design both for efficient function and for simple robot assembly. These robots are computer-controlled. They can be easily reprogrammed to assemble updated versions of this typewriter or totally new products. They bring automated flexibility into assembly. Certain jobs, like assembly of the typewriter circuit boards, can be done with a speed and accuracy which no person could match. This brings to the manufacturer advantages of better quality, reliability, productivity, and less labor. This factory is at the forefront of assembly automation in America. At present, it's unique. It's an indication that in industrial automation, redesigning the product for simple, cost-effective robot assembly is a productive way to go. That simple can be beautiful. That, though, can't be the total answer because many products are difficult to redesign. For example, some experts say that car assembly work of this type might best be left unautomated for humans to do.
The big advantage that humans have in a manufacturing environment is that they can alter their performance to take into account changes in the environment. For example, if parts don't fit quite right, they can change the way they try to put them together. The state of the art in robotics now is that robots can't come close to that sort of adaptive performance.
But advocates of all-out automation disagree, arguing a need for complex robots to replace people even on tricky assembly jobs like these.
I think we'll see a wide spectrum of sophistication in the assembly operation. Some jobs will be able to be done by relatively unsophisticated, what we call pick-and-place robots, while other assembly tasks are going to be more difficult and more complex, and they will require the more sophisticated robot technology.
For robots to do assembly work like these people, they would first need eyes to pick out the right pieces for the job. Vision is part of the more sophisticated robot technology. How would it work? And is it worth it? A human eye can easily recognize and pick out the right assembly part from this tray. But to the computer eye, the video screen, these are a jumble of overlapping shapes, difficult to analyze and recognize. Much more research into computer vision is needed to bridge this recognition gap.
To analyze a scene consisting of one part is relatively simple. However, if you have a scene consisting of several parts, especially if they touch or overlap, such as this one here, where you have parts on a tray, that scene is more complex, and it's much more difficult for the computer to discern that scene. When we see a circle or a circular object or a spherical object or a planar object, somehow our mind processes it on the basis of what we have grown up with, some kind of models that are built in our brain. We don't quite understand how we do it. That's the mystery of nature. Now we are trying to emulate it, thinking because just it's easy for us to do it, it should be easy for a computer. Ain't so.
Successful computer recognition of jumbled assembly parts still has a long way to go. But computer recognition of simple, distinct shapes is already being used in the next sector of manufacturing, inspection. Back here at IBM, they're inspecting their new typewriters with a simple computer vision system. The required recognition is limited to the letters of the alphabet and type symbols. It's designed to work simply, part of the whole approach of redesigning the product for simple programmable automation. However, in university research, scientists are working to duplicate the stereo depth vision which humans use in inspection work.
If you take a scene in which two objects are separated in depth, and you look at them first with one eye, and then with the other eye, you detect differences in those images. We're capable of matching up those differences and on the basis of that, computing depth in the scene. When we've got the depth data from stereo or whatever, our problems are only just beginning. Because what we really want to do is to compute symbolic descriptions of objects inside the computer. For example, we'd like to be able to compute a mathematical model of an object such as this coffee cup. We'd like to say that it has a body which is cylindrical, from which we drink, and that it has a handle which is attached in two places to the body, and that the handle is curved and essentially cylindrical. We'd like to have those kinds of models and store them directly in a computer and have subsequent instances of a cup matched up against those stored models.
In this way, a computer inspection system might, at very great expense, detect a chipped cup and reject it.
Unfortunately, systems like I've described with the cup are only available right now in a laboratory. To compute descriptions right now, even on simple objects, requires 45 minutes to an hour of processing, even on quite powerful computers. And we in this laboratory are building a computer that consists of 250,000 processors that are all interlinked, and which we hope that we'll be able to compute stereo in around 100th of a second.
This would need the development of the next generation of multi-million-dollar supercomputers, which are hardly likely to be cost-effective for inspecting cups. How far, then, is sophisticated technology needed to attain the greatest benefits from automation today?
Technology, supercomputer or otherwise, is not the primary impediment to the introduction of computer automation to manufacturing plant today. The main impediment is management's unwillingness to take risks and to chance doing things significantly different than they've been doing them in the past.
At John Deere, they have taken such a risk with a $30 million computer-automated materials handling system. Materials handling is the next sector of manufacturing. It deals with delivering all the parts and materials to the right place in the factory at the right time. In this half-mile by half-mile factory, the system is computerized. The parts start in one of 3 high-rise storage areas. There are 3,000 different parts in this one. The computer knows where each part is. It directed it there in the first place. When the production schedule in the computer calls for particular parts for a particular tractor model, these robot carts go into the store, pull the parts out, and route themselves through the plant conveyors to arrive at the right place on the assembly line just in time. This flexible system can reprogram the materials flow for changing production demands. It's the showcase of the just 90 such systems working in this country. It cuts inventory by 2/3, saving 10% of the production costs. Productivity is up because storing, moving, and tracking is controlled by computers and machines, not by manual or white-collar clerical and scheduling workers. In this sector of automation, traditional white-collar jobs disappear.
Many of the people whose job it is now to keep track of the factory will no longer have anything to do. And if you can cut out a white-collar job, you save substantially more money than if you cut out a blue-collar job in general. And anyone in the white-collar labor force who handles paper for a living has a job that's very vulnerable, because handling paper is precisely what the computer can do away with.
Computer automation, we have seen, is being brought into each sector of manufacturing. But the paper shuffling needed to run the whole system is still a barrier to a revolutionary increase in productivity. This barrier could, in theory, be overcome with the advent of computer-integrated manufacturing, a central computer replacing people and paper. However, such a central computer would need to embody the human understanding of how a factory system actually worked and be programmed to make decisions about what to do in any situation. This is exactly what Professor Mark Fox of Carnegie Mellon University is trying to set up at his computer. an artificial intelligence expert system to run a factory. But first, at his fingertips, he must have the understanding of how a factory works. Such human expertise and the responsibility for doing the job belongs to the factory production manager. In the factory, Professor Fox taps the production manager's expertise. Because running a factory is a shoot-from-the-hip affair, nobody really knows logically how to coordinate all the machines, materials, and people and their disruptions, breakdowns, and bottlenecks.
Now is a bottleneck. We've had a lot of problems this year getting the output to match our demand. It creates a couple problems for us and a couple concerns. One concern is feeding the bottleneck. Since it is a bottleneck and it's constraining the total output of the system, we want to maximize that output as much as possible. I see. The second thing we have to consider is
if an understanding of how a factory works could be put into a central computer, this computer could respond to and deal with breakdowns and disruptions far more quickly than any person. Manufacturing efficiency could then, perhaps, take its great leap forward to computer-integrated manufacturing, SIM.
yes, it does. A lot of things we have to worry about.
SIM represents to many, many companies a brave new world of manufacturing. It's a new technology, a new way of doing things. It involves changes in an organization's culture and in the organization's structure.
I think one has to be very guarded in their expectations for the application of techniques of this nature, expert systems techniques, artificial intelligence techniques. Guarded in the sense that they're just making it out of the laboratory. So if one expects that these techniques can be just picked up and used directly in the factory, then you're mistaken. There still is a great deal of development work that has to be put into these systems.
Developing computer-integrated manufacturing depends on getting a better understanding of how a factory could optimally work, and how that ideal could be translated through software into a central computer control system. Computer-integrated manufacturing, if it worked, might be the technological edge to boost productivity and make this nation's industry competitive with any other country. Yet today, computer-integrated manufacturing is only a theory. Of available computer automation, there are only a few showcase examples of excellence, representing little more than 5 or 10% of what could be possible. While there appears to be a trend toward computer automation, American industry has hardly started to invest in the basic technology.
Well-publicized showcase factories in the companies like John Deere and General Motors and IBM that are recognized as the leaders in bringing these showcase factories up to speed and using them. These showcase factories are not indicative of the rest of the country. Other companies in the United States can look to these factories as goals toward which they can strive.
According to this view, America faces an urgent and major program of reindustrialization based on computer technology and the redesign of products, equipment, and attitudes. But others welcome delay, arguing that advanced automation should proceed slowly to allow time for planning the transition.
What we have done here is secure people's jobs. Prior to going into heavy sophistication of automation in Chrysler, we were laying people off by the thousands. In the last 36 months, where our heavy automation program has bit, we have now been bringing back well over 1,000 people a month for over 24 straight months.
Computers can play a vital role. Automation can be central to this economy and used in a very beneficial way. But none of that's going to happen if we focus on all technological change as inevitably meaning progress. The future is not something that we can worry about in a few years. The future is upon us. The question is what that future is going to look like and what the human cost is going to be.
The availability of computer automation raises vital questions for American industry and society. Is computer automation really the key to revitalizing manufacturing? And if so, is it being adequately pursued? Certainly, leading companies plan to install further automation systems. automation seems to be working for them, and others are expected to follow. Yet are traditional market forces sufficient to drive enough companies toward this next industrial revolution? Or are greater government incentives called for? While studies disagree on the actual figures, substantial numbers of workers are likely to be dislocated. Will laissez-faire attitudes suffice during the transition period, or are special social programs needed? Should available jobs be spread through overall shorter working hours? Must industry or government undertake substantial retraining and relocation programs? These questions have yet to be sufficiently studied. They hang over the future of American manufacturing, over the ways in which the benefits of computer automation might be attained while mitigating its costs, over the need to revitalize American industry and keep Americans working.
For a transcript of this program, send $4 to Nova, Box 322, Boston, Massachusetts 02134. Please be sure to include the show title. This program was produced by WGBH Boston, which is solely responsible for its content. Major funding for Nova is provided by this station and other public television stations nationwide. Additional funding was provided by Allied Corporation, a world leader in advanced technology products for the aerospace, automotive, chemicals, and electronics industries. And the Johnson & Johnson family of companies, supplying healthcare products worldwide. To purchase film or video copies of this program for educational use, call toll-free 1-800-621-2131. In Illinois or Alaska, call Collect 312-940-1260.